So starting from today, we're going to dive into things related to machine learning, which is an important part of doing data analytics. Okay. So far, before today, we have mostly focused on explanatory and exploratory data analytics. Right? We know how to describe the data by calculating statistics. We also know how to do visualizations. Then starting from today, we're going to shift our focus to predictive analytics. Right? So it's basically to predict about the future outcomes, or sometimes to dig out some patterns useful for we to make some future predictions. Okay. Well, there's still much to be learned about things like visualization, data aggregation, because we couldn't have possibly covered everything. So when we are dealing with predictive analytics, from time to time, we're still going to revisit or introduce some new techniques about exploratory analytics. Okay? So, but the focus is going to be learning, starting from today's class. Okay? We don't really spend much time on prescriptive analytics, and that's mostly about optimization. There are other courses dealing with particular project. So for the rest of this course, we're going to focus more on making predictions. Right? In terms of machine learning for making predictions, there are generally two types. One is called supervised learning, and the other is called unsupervised learning. And we'll get down to those two important concepts as we progress further. But the main idea is that for supervised learning, there are some information provided in the data set that may be helpful for us to learn how in the data set the quantity we want to predict actually look like, how they are associated with the features based on which we want to make predictions. Right? And unsupervised learning is basically more about, we have a data set, we don't really have a very clear objective of predicting some quantity. Instead, we want to identify possible patterns in the data set. For example, we have a data set of customer records. We want to maybe do some clustering or grouping of the customers to divide them into several different groups, right? And then after we have several clusters or classes of customers, we can provide labels to those groups, and later on, we can further perform supervised learning on top of unsupervised learning. Right? And that's just a very brief and high-level introduction of those two concepts, and hopefully we'll get more details as we dive deeper. Okay. Speaking of supervised learning, there are, again, two subtypes of supervised learning. I think many of you may already have encountered those concepts in other courses or in your own experiences. One is called regression, and the idea is pretty simple. If we want to predict some continuous quantity, then it's called a regression plot, right? So, very simple example, if we want to predict the price at which we can sell a used car, and that's regression, right? Because price is generally considered as a continuous variable, right? It can be a continuous quantity. Another type of supervised learning is called classification. Very similar to regression, but the quantity we want to predict is discrete. By discrete, I mean there are several classes. For example, let's think about a mortgage broker helping customers apply for mortgage, apply for a loan, right? So we want to maybe predict whether or not a certain application is going to be successful. Right? And the outcome is going to be something we consider as binary, right? Either the application is approved or it is rejected. So 0 or 1, rejected or approved. So that divides all the application into two classes. That's something we call discrete, either 1 or 0. And sometimes it can be multiple classes. Right? So maybe predict customer choice of a product. The product may be a t-shirt. It has different colors, of the same T-shirt, red, blue, green, many different possible colors. And then out of those possibilities, which particular color will the customer choose? That's called a classification, right? Predict the class label. And the main library we're going to use in this part is called scikit-learn. Scikit means scientific kit useful for us to do some statistical or machine learning analysis. And learn means machine learning or statistical learning. Okay? So it's very common and widely used both by academics like myself and also data analysts who work in the industry. The good thing is that this package, like many other packages we have been using in this course, are included by default when you install Anaconda. But just in case you don't have it on your laptop with your Anaconda for some reason, there's a command for you to run inside the Jupyter Notebook so that it can be set up properly before we can use it. Okay. Now, we're going to dive into a specific example to learn the idea and techniques regarding supervised learning. And specifically, we're going to start with the simplest kind of machine learning, actually supervised learning, which is linear regression. I know that probably everybody knows linear regression, either from statistics course or from your previous background. But this time, we're going to see what are some the Python codes to implement linear regression, right? And what are some important concepts from linear regression that can be generalized to the general things related to supervised learning, right? Not just regression, but anything else. Okay, so here's a quick overview about the steps of doing supervised learning before we switch to Jupyter Notebook. Right? So as usual, we'll have tabular data. Usually we import a data set, and then we have a data frame. Right? In the data frame, we usually have multiple columns. Out of the multiple columns, one column is called the target variable. That's the quantity we want to predict. For this example, we're going to dive into, we're going to estimate the medical cost incurred by a certain individual. Right? So then the medical cost incurred for that individual for a year, that's something we want to predict. And then the remaining columns provide information about the individuals. And we'll see things in more details in a few moments, but that's the main idea. Okay? We have a response variable or the target variable. For some reason, the color is not very clearly shown here, but that's okay. And then the target variable can be numeric or continuous value. That's regression. And that's something we're going to deal with today. But there can be classification problems. Another important topic we're going to deal with, I guess, either toward the end of today's class, if we have some time after doing regression, right, or starting from after midterm. Right? And then we're going to do something called train test split. It means that we're going to divide the records or the rows in the data set into two parts. Most of the data records is going to be used for training, right? So for fitting the model so that it can help us make predictions. And the remaining rows is going to be used for testing. So the model is trained or fitted based on the training data, and then it can already make predictions. But after we have trained model, the model hasn't seen the test data. So to the model, the test data is something very similar to new records in the future, right? Not exactly, it's in the data set, it's in the past. But then to the model, it's something not seen, so we can use the test data to simulate the future and make prediction on the test data so that we can know how well the model can be expected to perform on new data points. Okay, some more descriptions are included in the slides, but we're not gonna go over everything in the slides. Instead, we're gonna switch to the Jupyter Notebook to hopefully understand everything by getting our hands dirty. Okay, so allow me a moment to find the Jupyter notebook I want to use. All right, as mentioned, the important thing before everything gets started is to imagine that you have a data set. Among the variables in this data set, one is the target variable, the quantity you want to predict. Right? The remaining are the feature or predictors in this data frame. Based on those features, we want to predict the target variable because the features will be providing important and useful information for how to make the prediction. Right? So let's get started by looking at the medical cost prediction example. So the context is that let's imagine that you are an analyst at an insurance company, right? So you are interested in predicting how much medical costs will be incurred by each policyholder. And that's a very important question to insurance companies, right? Because you charge the policyholders the insurance premium, and then once they go to the hospital or see their doctor, pay the medical bills, you will be paying most of their medical costs, right? So, to be sustainable in terms of your business operations and also profitable, right? So you want to make sure that the total insurance premium paid by customers is able to cover all the medical costs that's going to be incurred by the policyholders. Right? So that's the general idea. So the target is the annual medical cost. But as we imagine, so each individual, each policyholder will incur different amounts of medical costs because every person have different situations, right? So as we will see in the data set, we have information like age and gender of the policyholder, and BMI is the body mass index. That's some indicator of the health condition, right, for the policyholder, and how many children the policyholder actually have. Right? In some cases, well, if you have more children, intuitively, you have less time to take care of yourself, so you may face a higher medical bill. For some situations, maybe the children are also included on the plan, and the medical cost may be higher for those with more children. Right? So that's why number of children may be important, and also things like smoker, non-smoker for the policyholder, and also the region where the policyholder living. Like different regions may have some impact because if the policyholder is from a more wealthy region, maybe the health condition may be better, right? That's the general situation. So the reason we can use the data set like one including those columns to make prediction is because all those variables have some indications on the outcome, which is the medical bill, right? So by looking at the data set, we're going to be able to identify the relationships in the data set between those features and the outcome, the target. And then we can try to make generalizations. So we can identify the relationship from the data set using a model, and then going beyond the data set, we can use the relationship we identified or estimated to make predictions for, let's say, a new policyholder. Okay? So first of all, we need the data set. Then again, as usual, let's go to Avenue to Learn. So sorry, I'm encountering a little bit problem. Hopefully it can be fixed. Yeah, so I cannot access my data because I somehow am offline. Okay, so things should be okay now. So we go to content, and then as usual, data set for in-class examples. Okay. And this data set is the third data set among all those bullet points. To make things easier, let's just copy the GitHub link. And going back to the Jupyter Notebook, let's do, first of all, we need to import pandas, right? So import pandas as PD. Then we need to read the data set as a data frame. So for this part, let's give it a name. So I'm going to call it med_cost. Just for simplicity, not using a name that is too long. And we're going to do pd.read_CSV. That's how we load a data set, right? So I'm going to copy and paste the link to the data set on GitHub. Okay. And then after we load this data set, let's do med_cost.head to view a few lines in the data. Okay, so things went well for this loading. So as we can see, we have age, sex for gender, and BMI, number of children, smoker, yes or no for every individual, right? And the region in which the policyholder live in, and the charges. Last column is our target, and not always the last column would be the target, but in this case, it's the last column, right? The charges mean the medical charges, so how much medical cost was incurred by the corresponding policyholder. So that's our data set, all right? So after we get the data set, usually we need to do things like overview the data set and use the .info function, right? And check for any missing values, if there's any duplicated records. Also, if you want, you can use the box plot to identify the outliers. Okay? But to save some time, I'm going to skip those. After loading this data set, I actually pre-processed the data already, so there's no missing values and duplications, etc. So, two objectives for today's class. One is that we're going to develop a predictive model, right? To predict based on the characteristics of the policyholders. And then we want to get the target value, which is the annual medical cost. Right? In the data set, everything was given to us, right? But then this is mostly for us to identify the relationship between the target and the features, right? So that when we have new data points, we want to predict the unknown annual medical charges based on the features of a potential client. Okay? And then after we made the prediction, we want to also evaluate the performance, like how accurate is the model. Okay, so those are two objectives. Do we have any questions so far? All right, so let's get started. Now here, just to do one thing. Import sklearn. Okay, that's the package that will enable our modeling and analysis. Okay, if you get an error, I mean that it's not installed, then you can use this command to install it. Right? Pip is the package manager of Python. Make things very easy to install. All right, so we're going to do the predictive modeling, but before that, let's actually do something that belongs to the category of, exploratory analytics. Something I think interesting, but we haven't done before, right? So, how do you think we can predict what? I mean, maybe I should say, why do you think I can predict the target value based on the features?
Is there some sort of
correlation, right? Because they are correlated. Like age is correlated with the medical bill. Right? That's why we can use age as a predictor to predict the medical bill. Right? So before doing predictive analytics, it's generally a good idea to identify the correlations between the variables. Right? So what we can do is just to use a simple command. Right? Data frame dot CORR, that's the acronym for correlation. Right? So our data frame is named as metcast, right? And then dot CORR, round brackets, and let's see what we get. Sorry, some error, so let me quickly check. Oh yeah, so I remembered. So why do you think we get this error? So calculating correlation for this data frame, what problem do you see directly? Yes, please.
There's non-numeric data.
Yes, exactly, right? Because we can only calculate correlation for numerical values. So what do we do?
Like numerical mean.
Exactly, right? Something we have done before. So numeric only equal to true. Okay, so now we get a nice looking table, right? So the row indexes and column indexes are the same. Those are just the names of the variables in this data frame, right? Let's say we focus on let's focus on the last row, right? Charges, because we do want to know if the target variable is correlated with other variables. So as we can see, for charge and age, so we're going to look at the intersection of the charge row and age column. We see this number 0.29, right? It's a positive correlation. Correlations, and those are correlation coefficients between -1 and +1. So almost 0.30, right? So that's some considerable amount of correlation. Actually, it's positive correlation, meaning that if the client, the policyholder, is older, then the medical charges tend to be higher. Right? That's the meaning of positive correlation, right? And same thing for BMI. If the BMI is higher, maybe the client tend to be having some overweight issues, and then it's intuitive that the medical bill is also going to be higher. The number of children also affects the medical bill positively, but not too much, right? A small amount of correlation. I mean, we can guess that maybe the children's healthcare bill is not directly included. It's just that some very moderate effect of having more children allows you less time for taking care of your own health, right? And charges, that's a perfect correlation because that's the same variable, right? So of course you can also try to see the correlation between other variables like BMI and age, BMI versus children, right? But the most important thing here is to see how the predictor variables affect the target variable, right? So now we can be assured that those variables at least have some amount of correlation with the target variable. So maybe it's a good idea to include them in your predictive model. Okay, so let's do one more thing. Let's do visualization. So let's import the package Seaborn. And remember, Seaborn was the visualization package for creating plots. Not usually, but in this course, mostly we use the matplotlib. But then Seaborn is a very widely helpful package as well. So let's do SNS.heat map. But before that, we actually need to do something else. So let's say we need to assign this outcome of the correlation matrix to a certain variable. So I'm going to just call it correlation matrix and run it again. And then for the heat map, we're going to just use the correlation matrix we just generated as the input to the heat map. Right? This does not actually do much, but we will see that it's actually somehow make things slightly more intuitive. Right? So let me also import matplotlib .pyplot as PLT. Right? So it's generally a good idea to import matplotlib, even if you are using Seaborn, because they are really the same thing at the core. Okay. So this is the outcome, right? It's nothing, I would say, nothing new compared to the correlation matrix. I mean, it's still a matrix, right? It's just we're using some color code for every coefficient of correlation, right? And on the right-hand side, we can see the color map, something like a legend, right? So as we can see, going from smaller correlation upwards to greater positive correlation, the color becomes lighter. So it means that if we see lighter colors in the matrix, then we have a stronger correlation, right? So let's focus on the charge row. For charge and age, we have something like somehow lighter purple, right? And the color maybe here, some value around 0.3, 0.4, right? For BMI, it's going to be a darker color, meaning that the correlation is even smaller. The lighter, the stronger the correlation according to the color map on the right-hand side, right? So the children and charges, and the color is kind of almost black, but it means that the correlation is actually somehow low, right? And charges is almost white. It's the stronger correlation because that's the same variable. Okay, so that's I mean, here maybe it's even more intuitive to look at the correlation matrix directly, right? But as you can imagine, if we have a more complicated data set with like maybe more than 10 variables or even more variables, and then it's difficult to digest very quickly about all the numbers in the correlation matrix, right? In those cases, the heat map will be more helpful. Okay, so do we have any questions? All right, so now we're going to start the predictive models. Okay, so here's the main idea of supervised learning, including linear regression. So what is the predictive model? There's a lot of mathematics behind every single machine learning model. Fortunately, we don't really need to digest all the complicated stuff behind scenes, right? So for our purposes, I would say that we can think of a predictive model to contain the parameters. Right? When we change the parameters, the result of your prediction may be different. Right? For every model, generally we're going to have some input, which are the features of the records. Right? For example, policyholders, age, BMI, number of children, those are features. Right? And then we feed those inputs into the model, we'll get our prediction as outputs. And then a model is characterized. Yes, please.
So based on the correlation that we saw in the earlier slides,
Yes.
each of the individual variables, they didn't have a particularly high correlation with the outcome. Like less than 3.3 for each of them, right? So why are we confident in the overall outcome based on the inputs if the inputs themselves don't have a particularly high correlation with
Yeah, so that's a very good question, right? I mean, I think I may need to respond by 2 points. First of all, individually, they may each have limited predictive power, right? But combine them together may give you stronger power. Okay, that's the first reason. And the second reason is that, particularly in this example, you're actually right. As we'll see, the first model we're going to use will not have very impressive outcomes. That's because, can you guess why?
These are not good predictors like the inputs themselves.
Yeah, exactly. Because we did omit some categorical variables, right? So, I mean, to illustrate the idea of correlation, to get started, we actually only focused on numerical attributes. And later on, we'll see the categorical variables actually are very important. Okay, I mean, later on, I will go over the parts where we actually need to convert the categorical variables to numerical variables. And then if you want, you can visualize the correlation again. But it will be much stronger. But then the idea is still that sometimes we have to develop model in an incremental way, right? I mean, because initially we don't know much about it. Even though correlation may be weak, still may be playing some kind of role when you combine them together, right? So then we we always need to do a lot of experiments, like including certain variables, maybe making the predictive power or performance better. But sometimes including too many will lead to overfitting, making everything even worse, right? So it's all complicated. We have to do a lot of trial and error. And then today we're gonna just do a little bit. And we'll just leave more details to later parts when we look at more models, and also on your own when you're solving problems, including the group project and other situations.
Okay, so assuming computing power is not an issue, like assuming like you have infinite computing power.
Yeah.
So is there a point if you keep on adding more variables, like so your outcome might actually start to become less accurate?
Very good point. So the answer is that depends on your data set, right? If you have infinite data, you want to include infinite variables, just like neural network. So because the neural networks, the deep learning stuff, which are very popular today, they have billions of parameters. That's very complicated models, right? They get billions of predictors. So, but then if you have a small data set, they don't work. They lead to overfitting, right? So the idea is that depends on how much data you have. In general, you may want to have more data, but not always. It depends on how much data is available to you. So for a given data set, there's always going to be a trade-off. And actually, we're going to spend time on that. It's called the trade-off between variance and bias. Or sometimes we say the trade-off between underfitting and overfitting. Okay? Yes, please.
See, when you do run into a situation like the one that you just stated, right? So where you have many different predictors. So, in my opinion, I guess you can kind of weigh in on that as well, and maybe let me know if that's the correct approach. So would you first run a correlation and then figure out which one have the highest correlation, then just use those specific predictors, and then just discard the other ones?
Well, that's one approach. So that's one approach. Intuitively, that's a good idea. Right? So you just filter out all those strongly correlated predictors. I mean, you can try that, but that's typically not the whole thing. Right? So because things are pretty complicated, right? So you don't know for those predictors you discarded, maybe they don't play much role if you investigate the individual or pairwise correlation. Because all the correlation matrix has done is to show you the pairwise correlation, right? So if you only consider, let's say, the medical charge with let's say, number of children, it's a small correlation. But remember that we don't know how things will be different if you combine maybe number of children with other factors, let's say whether or not this person is a smoker. Right? So that's an intuitive approach. You can try it out. I mean, the key trick for doing all those predictions, learning stuff is to do a lot of experiments to see what works best for them. Right? But that's typically the case that you also need to try other methods. Right? So actually, later on we'll see there's a way already implemented by developers to do some parameter or model tuning to help you select parameters instead of starting from scratch. And we'll just dive that a little bit as well a bit later. Okay, thank you for the question. Any other questions? Okay, before the break, let's just develop the main idea of supervised learning. Right? Every model is characterized by the parameters. If you change the parameters, the outcome will be different. The performance of the model will be different. For example, linear regression, right? I assume that everyone knows about linear regression. We're going to predict the response variable, the target variable. Here it's the medical charge, right? And typically we denote that by Y. And the features are denoted by X's, right? Age, BMI, number of children. We're focusing on those for now. Okay, so the linear regression says that I assume the medical cost is a linear function of the predictors. Right? And A0 is the intercept, A1, A2, A3 are the coefficients corresponding to age, BMI, and children. Right? So for example, A1 measures the degree to which age is affecting the medical cost. So if you choose different values of A0, A1, A2, A3, the model is going to be different, right? But how do you know which combination of parameters will work the best for you? it's going to be based on the actual performance, right? So the main idea is that you pick up some possible values for those parameters, coefficients and intercepts, right? And then you try to see the model performance to see what the model predict for you in the training data set matches well with the, the target variables provided in the data set, right? If not, you should tune your parameters, change your parameters to improve the performance, right? And the training is to try on different values of parameters. Eventually, we want to be able to identify a good combination of parameters that gave you reasonable, prediction performance. Yes.
In here, so like the different A values, are they just the weights for the different inputs?
Yes, for linear regression, it's the case.
Okay.
Yes, because it's very simple, right? So if you increase age by 1 year, let's say A1 is 100, then it means that if you're 1 year older, you're expected to incur $100 more than 1 year ago, right? But that's the simplest machine learning model you can get, right? So things are much more complicated for more general models.
And how are the weights set? Is it the program's job to like try out different weights and see what works?
That's basically the idea, right? So for linear regression, we have the something called the what do you call it? The least square method, right? So you're trying to measure the gap between your prediction and the actual observations in the data set, right? So then there's some algorithm for you to minimize this gap. And what this optimization algorithm minimizing the gap does is simply to try out different values of A0, A1, A2, A3, eventually reach at the minimum point, right? Which combination of those values will help you minimize the gap between your prediction and the observations. Okay, thank you very much. Yes, please.
Yeah, like in this case, like for a linear regression model, would that just be your coefficients? So A1, A2, whatever the coefficients for those like variables would be. So that's just basically those numbers.
Exactly, right. For linear regression, the objective, not objective, but the main step is to figure out the values of those A0, A1, A2, A3. And then once you have those values, you have a equation, right? So then if you have a new data point, a new policyholder, let's say 50 years old, and BMI 19, children, number of children 0, and you can plug in those predicted values and calculate the target value as the prediction based on this equation. Okay, thank you for the question. So let's do a break for 10 minutes. So let's come back at 12:32, and then we'll continue with the linear regression model.
You're going to spend probably a couple hundred there.
I mean, if I can help, I'm not sure.
I definitely it's related to the coursework. And with my poor English, I speak Chinese.
I may respond in English.
Actually, we're learning machine learning as well, but in this, and we learn like a thing like PCA analysis. So we just wanted to know what the principle of that analysis, because I thought they combine like those 23 variables into like 10 components, and what's the meaning of the area of the each of this. So we just wanted to know like the basic principles. So
the main idea of this.
yeah, the main idea, how they transfer those variables to the.
That's actually it's rather complicated, I would say. But when it comes to Python, you have that package available. Right? But the main idea is that it's called dimensionality reduction because you have so many variables. Well, I mean, there may be too much variables, making the problem too complicated and not capturing the essence of the problem. Right? So it's like you can intuitively, I would attempt to think that, let's say you have 100 variables, right? But then you think there's too many variables, you want to make it simpler. Right? So maybe the idea is that, okay, for the first 3 factors, maybe I can combine those into one single variable. It's like you're doing some, what do you call it? So not exactly clusters, linear combinations, right? So you actually usually you do the weighted, combinations, like predict 1, 2, 3. You figure out a way to combine those. It's typically A1 times predict 1 time plus A2 times predict 2 plus A3 times predictor 3. And then you add them together, that's a new predictor. And then you do similar things for other predictors.
Okay.
Right? Eventually, I can reduce 100 predictors, let's say, to 5 predictors, right? So then the 5 predictors will be, not capturing, of course, everything, right? But it will capture, maybe 70% of the predictive power.
Okay.
So that's the way they selected is that, okay, it's more like a change of the axes, right? So basically, right now you have the predictors being natural predictors like age, blood pressure level, those kind of things. After you do PCA, things are more obscure, but you do reduce the dimensionality. Right? So because you want to figure out a direction on in the space of the data points that captures the most of the variance. Because the predictors, they are providing a lot of variances, right? Because imagine that people are different in terms of outcome because they are different in their features, right? And then you want to find out the direction. Direction means that you can think about 2 dimensions. 2 dimensions, like one dimension is age, the other dimension is number of children, just borrowing the term here, right? So then you have 2 dimensions. But then along age, along number of children, like you have some variations, but the variation is not so big. Right? Instead, you want to combine them, so you have that sort of sloped line, and you move on the sloped line, the data points are more spread out. Right? So it means that along this direction, people are differentiated from each other more. Right? And then that's the way you want to define the new direction as a new predictor, because if you use that predictor, you can differentiate people much more than the natural predictors. So then you combine them and introduce them into a new predictor. And then maybe using only one predictor, you can already capture like 80%. Let's just take an example number. 80% of the predictive power of consider both age and number of children, right? So in that case, the problem got simplified. You reduce the 2-dimensional problem to 1-dimensional problem. It's not a big deal in this 2-dimensional case, but imagine that you have 10,000 dimensions. It's going to be too complicated, right? So maybe you reduce it to 100 dimensions. So that's making the problem so much easier.
But how they select which the variables they can combine together?
Yeah.
By what base?
The main idea is to select. First of all, I'm step by step. Right. First variable should be, if you look at the combined predictor, people have. Records will be more different along this combined predictor. Right? Maybe for age, like they are ranging from 20 to 60,
yes.
So the spread out is 40. Right? But then for number of children, the spread out is from like 0 to 5. Let's say. So that's a moderate spread out. Right? But then if you combine them, let's say 0.5 times age plus 0.5 times the number of children, right? And then that's a new variable. You can give it a name, say that weighted age and number of children, right? And then you can look at the possible values. You find that okay, now the spread out is much bigger. Like the spread out is like it's 100 instead of it's larger than both. Right? And then that means that people can be better distinguished using your new predictor. So maybe the new predictor is already capturing most of the performances by the 2 predictors combined. It's not going to be better than the 2 predictors combined together because the 2 predictors combined together already provide everything you have, every information you have for the new predictor, right? But then it makes the problem simpler. So you want to capture the essence. So you can answer questions like, okay, actually the way I'm gonna select, maybe approve or reject a policyholder's request is based on this new predictor. That, because that captures the essence of the problem, and so that makes it easier to interpret. Right? Yeah.
And to break down the specific question,
Yeah.
so I just mean that in this question, we need to choose 10 component as.
Yeah.
Can we understand like components is the new variables, or so like why it comes for the array, and each array we have like 23. So what numbers are 23 of that? Because in the
Yeah.
choose x. For x1 we have 23
Yeah,
dimensions.
because that's I think that the dimension, if I'm not wrong, so the original space of feature is still how many predictors do you have, like
20. We need to choose 10.
out of 23, right?
Out of 23.
Yeah, so you have 23 values. It's still gonna be those 23. Each new variable, each new predictor is still gonna be having 23 entries, right? It's just a vector. It's a point. It's a direction. It's a vector in the new dimension. Right? So it's a combination of the 23. So it's kind of like So basically,
It's a
combination.
This 23.
Yeah.
For example, like we choose 10 from this
Yeah.
variable.
Yeah.
And this array just show that there's 10 array, and each array just has 23
Yes. So
entries.
every new predictor, every new TCA component, right? So that's still a vector. Everything is a vector, 23 element vector. But then you have 5 vectors, and that 5 vectors will help you do the prediction later. So basically, you can project any new data into the combination of those 5 vectors. So it's
I can understand that is the array actually is the new variable.
Yeah,
so we
new
have
variable,
10 variables now, but in each variable we have it for like 23 dimensions.
Yeah, exactly.
Because it includes 23 columns.
Yeah.
And once we wanted to know, okay, so for each array, like for each variables, we want to know the variance, like how each component you contribute to the y.
Yes,
So
exactly.
we know the variance ratio here. So this is the weight, the coefficient estimate for the variables.
Yeah.
Okay, I understand. Okay.
Yeah. So let's say like the age is age is 0, 1, right? And the number 20 is 1, 0, right? Because you only focus on one entry at a time. And then you combine them together by doing some linear combinations. So some coefficient times age, some coefficient times number of children, and then you get it's still a two entry variable, right? But then you have a number in each of the entries.
So that's why those numbers is different than our original database, because it's already be projected to the different dimensions. So it comes like new numbers, new variables in this area.
Yeah. I'm just curious, what course is this?
It's big data in finance.
Oh, okay.
But it's too advanced. So that's why. And we also learn like random forest something.
Yeah, we're gonna come back to that. Hopefully that will help you clear
But it's
confusion.
helped a lot. Yeah.
Okay.
Professor, you teach us so good.
Thank you so much for the
So
nice words.
good. A lot.
Okay. Thank you.
That would be handy. I'm not sure.
Yeah, basically, true means that cell is a missing value, right? So it's missing in the data frame. So false means that it's not a missing value. You're using the function not in the. Yeah. Okay. Thank you. Yes. Yeah, I think it's not. But you need to develop some degree of. I believe so.
So,
If we had an existing notebook open, like assignment one, like I said, or all the handout. Yeah. I use VS Code though. Then you have all the so can we do a split screen like VS Code and then go on the other side or whatever we're gonna do? I see. Okay.
Okay, everyone, let's get back to the class. So before the break, we have some. Before the break, we have mentioned the main ideas of supervised learning, specifically use linear regression as an example. So the idea, I believe, is pretty simple, right? So you want to change the parameters so that your model outcome also changes. And then among all the possible outcomes, you want to find the best outcome that minimizes the gap between your data and your prediction. Right? Once you achieve that, we say the parameters are settled and the model is trained. Then we can use the trained model to make predictions. Okay. So let's start to do the model development and training. Okay. So the first step is to prepare the data to separate out the target variable, the quantity we want to predict. So we're going to call that y, and y equal to med cost. That's the data frame name. Okay, and the target variable is called charges. It's the annual medical bill for the policyholder. Okay, and then what we are also going to do is that we're going to let's first actually visualize the data frame again. Okay, so because there are category variables we need to deal with separately. So for now, for the first step, let's focus only on the numerical values. So we're going to select age and BMI, children. Okay, only those three variables for now. So use square brackets to select columns, right? And inside the square brackets, we're gonna do a list of column names to select. So age, BMI, and children, including quotation marks, because those are column names. Okay. So let's see. Now we have selected those three predictors. Right? Then we're gonna assign them to some value called x. Right? So we have y and x. That's the conventional notation for target we want to predict and the feature columns. Right? X would be the combination of all the feature columns we want to use. So let's actually print out the head of x. So we run this command, and we can see that x is just a data frame of three columns. Right? So that's to set up the data. Yes, please.
So here we don't have a lot of columns, but if we have like many columns, do we have to manually pick out the columns that we want to include here? Can we not?
Oh well, sometimes yes, right? Because you want to, if you want to use specific columns, you have to use a way to single them out. If we want to select only the numerical columns, there's a command actually inside my PDF handout to just directly automatically select all the numerical columns. But then sometimes you have to do that, right? So sometimes, or you're using an automated procedure already implemented as a Python library to select the best predictors, and that's automatic.
Okay. In this example, for instance, we can use the numeric only.
Oh yeah. So if you want to see it, I'll show you. Okay. So let me change this. Let's say I'm gonna change the numerical only. So it's not directly numerical only, but Okay, so in that it's slightly complicated, but then let's do this. So first of all, I need to do. Let me remove this metcost.drop the target value. Okay, because the charge is the target value. We first drop it. Okay, so that's always something to do manually. After I drop it, I want to select the numerical attributes only, and there's a way to do it. So x dot select underscore d type. D type means data type. Okay, and then we tell the Python interpreter about what you want to include. So include a list of types, and here number. That means numerical only. Okay, so that's the command to do. And then we are gonna let this command output from this command to override the original x. And then we can do x.head. I think we'll get the same thing. So let me try to see. Which one? Oh yeah, D types. Yeah, sorry about the type. Yeah, sorry about the typo. Yes, exactly. Thank you very much. Yeah, so basically it's the same thing, right? I mean, well, this is the name provided by the developer. We have no choice about how to, define the name of the method. But this is the method to use.
Is the command part of the library, or is it like built in?
Oh, you can see X is a data frame, right? So
Yeah.
this is a command associated with data frame. So it's part of pandas, right? But you include the pandas, it's already included. Because the pandas give you the data frame and all the methods attached to data frames. Okay. Anyways, that's the result we want to have, right? That's X and Y as the features and the target variable. The next step is to do a train test split. Sometimes people also call it the holdout method. Right? The idea is something I just mentioned. So we have a data set. We want to cut it in half. Not exactly in half, but split into two parts. One part is called the training data. That's something we're going to feed into the model to do the training. Okay? And the remaining is reserved for testing. And the main idea is that we cannot let the model do the testing based on the data it has already seen, right? Because the purpose of training is to minimize the training error, right? So you already minimize the error, you already see the data points. It's not good for future predictions, right? Because you can't be the judge and the player at the same time, right? So we're going to reserve the testing data for performance evaluation, okay? So that's the main idea. Here, for illustration, I'm just showing you to cut the data into two parts, but what it actually works is not exactly the first few rows as the training, the last few rows as testing. It's all randomized, right? It's just selecting randomly a portion of the rows as training and the remaining portion as testing. Okay, training data for fitting the model, testing data for evaluation of the performance. Okay, so let's try to do the train test split. And to do that, we actually need to import another method. So for sklearn, it's slightly more complicated than the modules we used before because you don't just simply import sklearn, but then sometimes you have to import the submodules inside sklearn. So this time, there's some module called model_selection. And then from that submodule, we're going to import a function called train test split. Okay, so now we can use the train test split function, and this function is going to be applied to both x and y because we want to split the whole data set, including the x part and the y part, into two halves. Right? Not halves, but two parts. Okay, and then the output will be 4 different variables. So we'll get something called xtrain. That's just a name, right? That's the train, the feature part of the training data, the predictor part of the training training data. You can call it other names, but that's the most intuitive name. And then we have X test. Right? The remaining part of the feature data is called X test. And then we have Y part, Y train, and Y test. Okay, and then that's the results we need to collect from the output of this function. Then on the right hand side of the equality sign, we do train, test, split, and we do X and Y. That's about it, but there are some keyword parameters useful. Right? So first of all, we need to tell the command, how many data to reserve as the test data. So typically we specify a fraction, right? So it's for example, a rule of thumb can be 20% of the data, but we can use more or less, right? There's no firm rule to be applied, but then a good idea, a good rule of thumb is going to be 20% or 30%. Right? The remaining 80% is going to be the training data. And then there's something called random state. Random state is something you can specify as an integer, right? Here I'm using random state equal to 42, or you can use like 999, 999, anything, right? So the idea, it's actually called this, seeding for the randomization, because the split is going to be random, right? But computers, they don't do real random things. It's all simulation. So if you don't specify random state, everything will just work the same. But next time you run this command again, it gives you a different split. Right? So if I use the random state equal to 42, if you keep the 42 fixed, then every time you run this command, it's randomized, but it always gives you the same split. Right? That makes your result to be reproducible. Right? So next time you want to have exactly the same split, and then you will do this. Yes, please.
So alternatively, to get the same result, can we create two separate data frames, like one for the test result and one for
well, like
results, instead of using the random state?
Yeah, I think because this is typical paradigm, right? So you have feature and also the target, right? So I think this is sort of the norm of it. But I mean, I'm not exactly sure because there's too many things going on. We need to dig into the manual to see if there's other approaches to split. But yeah. But I think it's a good idea for those tabular data structure where you want to predict a column based on the features. Okay, I think that's the best way to do it. Okay, thank you. All right, so let's try to run it. So there's no error, but let's try to, for example, we can quickly visualize the training data. So make it smaller. Maybe xtrain.head. As we can see, after the split, it's still data frame, right? It doesn't do much else other than splitting the data frame into two data frames. Then X test. Well, that's another different data frame, right? So, but they're all coming from the original data frame. All right, so now we have the train test split. The next step is to focus on the training data so that we can fit the model. But before fitting the model, we need to create the model first. And we need to create a model, and then we want to fit the model to the data, which is we call the training. Then we can view the results and make new predictions based on the model we have trained. Okay, so that's the general steps for doing things. So let's try to create the model first. Again, we have to create a linear regression model. We have to import some submodule of sklearn. So sklearn from sklearn.linear model, and then we import linear regression. That's a function for you to create a model. Okay, so I mean, linear model is not only for linear regression. I mean, there's a class of models which we call generalized linear model, which include linear regression as the simplest model. Okay? So that's why we need to focus on this class of models and single out the linear regression model. So let's create a model. So you can give a name to the model. I find it simpler just to call it a model. But then if you are creating several models in the same notebook, you have to do some customization, right? Maybe model 1, model 2, or linear regression model and polynomial regression model, things like that. But here we're focusing on one model, so let's just do linear regression. Sorry. Okay, so it's as simple as that. Then it's created. Right? No error means that the model is created, but here there's no data fed into the model yet, right? So it's just a framework, the mathematical foundation underlying what you want to use. Okay, so that's the model, just the creation of the model, and then you need to fit the model, right? Creating the model gives you nothing because it's just the math framework behind the scenes. But fitting the data to the training data set is also fitting the model to the training data set is also quite simple, given that we have already been given results, developments based on the existing libraries, right? So we're going to fit it to the training data. The training data has two parts, which is the X part, the predictor part, right, and the Y part, the target variable part, right? So in the training data for X and Y, for every combination of feature, we already observed the outcome, and we want to tune or train the model so that the prediction of the model will be as close to what's in the data set as possible. Okay, so let's try to run this. Okay, so it's pretty quick because the data set is not too large, and linear regression is a relatively simple model. So it gives you some simple like table display, and that means that it's trained successfully. Right? If you run into a problem, it will give you some warning or error. Yes, please.
Can you go back to please? How does the command know which is the X variable and which is the Y variable? Is what order we put it in?
Yeah, exactly. The first is X and the second is Y, right? So that's how, because by the way, for any function, there are two kinds of parameters. We know the keyword parameter, right? And we also have something like those. We don't specify the name of the input. That's called the positional variables. So the positional variables have fixed order in your inputs. Right? You cannot, mess up with the order. But the keyword variables, like, for example, things like color equal to red, and you can include it any position after the positional variables. Okay. All right. So that's the fitting. It's also done. Now we can examine the result of the fitting. Okay. So let's do this. For linear regressions, it's actually just the A0, A1, A2, right? The coefficients and the intercept. So what we can do is that we can print. We don't have to use print, but this time I want to actually I want to print more than one line of results. So I want to use the print function. So model.coef and underscore, and that's how they just named it. Right? So that's the coefficients of the model. If we run this, it will print out the results. Right? So those are A1, A2, A3, corresponding to the coefficients of, I think, age, BMI, and number of children. Yeah, if I remember the order correctly, it may not be the case. Right? And then there's the model.intercept underscore. Sorry, typo. So this minus 5,095, that's the intercept, right? So that will actually give us the idea of the equation for the linear regression, right? A0 is the intercept, A1, A2, A3, and those are just the numbers in this list called model.coef underscore. Okay, so actually I didn't include this part correctly, so let's this part we can use so let me do this. So, to make things more intuitive, I'm going to show you a simple method that can actually, print out the outputs in a nice format, right? So this time I'm going to use the print with the f string But before doing the print function, maybe I should do A0. Let me define A0. A0 is the intercept, right? So I'm going to do model dot intercept underscore. Right? A1 is equal to model dot coef underscore, and that's the first coefficient. So the the index is 0, right? So let me copy this line, and then I define A2, the second coefficient. Let me do A3, the third coefficient, right? So now I have defined A0, A1, and 2. I can do an F string. Right? So I will say that the fitted model is y equal to A0, but A0 is a Python variable, right? So just to put them between the curly brackets, plus A1 times X1. X1 is simply, anyway, let me do X1, okay? A2 times X2 plus A3 times X3, okay? So then let's run this. Sorry about that, it's dot. All right, so that makes things a bit easier, but I mean, it's too many digits, so I think I did this in one of the suggested exercises, right? I mean, A0 has so many digits, and we can do 0.2f after the column, so that will only display 2 digits. Same thing for A1, 0.2f, so it's a floating point with only 2 digits, and 0.2f for A2 and A3. Okay, that makes it look nicer. So that's, I mean, F string is always quite useful in terms of making the outputs more intuitive. And there are other approaches we will see later, okay? So now we know that the impact of, impact of the variables. So X1 is age, and then BMI, X2, and X3 is actually number of children, right? We already see that actually what you get from the correlation part may be somehow different, because number of children has a weak correlation, but here the coefficient is actually quite significant, right? So it's 690. Yes, please.
Which command do we use to get the coefficients? Is it the dot fit command that we used earlier?
Oh, you fit the model, and the model will just do some adjustment, right, to change the value of the coefficients, and then model after training model dot coef underscore, that gives you the coefficients as a list of numbers, right? The coefficients are here, right?
So if you run the same thing again, you're going to get different coefficients, or is it going to be the same coefficients?
Well, I think it's the same because for a linear regression, the fitting is not randomized. It's just the least square. Right? Minimize the gap. Okay. All right, so now we can actually do prediction for new data points, right? So the model is trained, so it means that I can use the model from now on. Let's say we have a new policy holder, 37 years old, BMI is 27, who has 1 children, okay? 1 child. So we want to predict the annual bill for this person. How do we do that? It's just a simple command. But before using this simple command, we have to define the new client, right? New policy holder. So I find it useful to define a new data frame, which is a row of the characteristics of this new policy holder, right? So we're going to do pd.dataFrame. That's to create a data frame, okay? And then remember, we can create a data frame from a dictionary. So I can do age equal to this person is 37. Well, I mean, in the dictionary, after the column name, we have to predict a list, which is the column. But now we only have a list of 1 entry, right? Because that's just one new client. If you want to predict for 2 new clients, and then you can do 33, 37, maybe 42 if the second person's age is 42. All right, so then after age, we have BMI equal to 27, also square brackets. And then the third one, column name children, 1 children. Okay, so we can see yeah, so we should use a dictionary, right? So inside the square brackets of the function, we should use a dictionary. Okay, so that's the new data point we created. One row only corresponding to one new policy holder. You can use 2 rows or 3 rows, right? If you have multiple, predictions to make. Now, after we have this new client, what we're going to do is to do the predict using the model. So let's see how we can do the prediction. So we're gonna do model.predict of this X new policy holder, right? So you can see we have a number given to us, which is an array including 1 element, because we only want to predict one thing, which is the medical charge. So this person is predicted to have this medical charge $11,483. I mean, there are some many digits which is not realistic, right? We can do some rounding, like what we have done, because you cannot have more than 2 digits for a dollar amount, right? But anyways, that gives you the idea. So create a new data frame. I mean, you can do an array as well if you want, but I think this is better for visualization, right? And then just to use model.predict on this new data point. Okay, questions? Right, so we trained the model, we made new predictions of the model, and then we want to evaluate the performance of the model, right? Because even though we can make new predictions, but we have no idea if that number, about $11,000 for that new person, is that accurate, not accurate? We don't know, right? Because a policyholder comes in, there's no medical bill seen for that person yet, right? So we have no idea. We're making a prediction. So the main idea of having some sense of the performance or accuracy of the model is that maybe we can look at the test data. As mentioned, the test data is not already seen by the model, so it's simulating the future. It's not in future, but it can simulate the future. So this is the data frame. We constructed testing data. And so if we remove the target column, then we are left with the predictor columns. And just like what we have done, we can make a prediction on those feature columns. Right? And then I will get the corresponding predictions of the medical bills, annual medical bills for all those individuals in the test data. Of course, as you can imagine, those are going to be very different numbers from the actual observations. Right? Your prediction is never going to be perfect. But at least we can compare the actual observations in the test data with your predictions and to see how large is the gap. And that will help you gauge the accuracy of the model. Right? To measure the gap, there are a bunch of possible performance metrics. And for linear regression, the most useful ones, first of all, mean squared error. Right? So we know mean squared error is for every row, we compare the gap between your prediction and the observation, and then we square it, and then for multiple columns we sum up the squared values. That's called divided by the total number of rows. The average of the squared errors is called mean squared error. So that's one direct and very common way of measuring the gap, or something called R squared. Right? I think those are familiar terms from statistics. For our purpose, not that important for you to understand the very specific details of the meaning, but then it's also helpful to understand the meaning of R squared as well, because R squared is basically looking at the percentage of variance in the target variable explained by the predictors. Right? If you don't have the predictors, you can calculate the variance of the target variable, but then now you are predicting based on the predictors. Right? Now you have, if you have the the predictor values and predict based on the predictor values, you're supposed to reduce the variance. right? Because you're removing uncertainty. So R squared value give you some idea about what percentage of variance in the target variable is explained by the difference in terms of the features, right? Because if people differ in age, BMI, they are supposed to be different in the medical outcomes, right? So how well is your model explaining the variance? So let's get down to the detailed procedures to get things done. Okay, again we have to import some submodules from sklearn dot. This time it's called metrics, right? Because we are measuring the errors. From sklearn.metrics, we want to import two things. One is the mean squared error. The other is the R squared, right? So it's called R2 score. And then we can directly use those two functions to calculate the values. So let's first import those packages, and then we're going to use them to measure the gap between observation and prediction in your test data. Okay? So there are three steps. First of all, we need to predict on the test data. We haven't done that, right? Even though we have done it on a new data point, but haven't done it on the test data. So it's the same. It's going to be model, the trained model, dot predict. And then the prediction is based on the feature vectors, like the X text, right? Inside the test data set, that's our focus for measuring error. We want to look at the feature and then make prediction based on the feature and the fitted model. The results will be some Y variable, and we're going to call it Y predict. Right? It's going to be basically the Y pred is going to be the predictions in the format of a Python series. It's going to be a column of numbers. Okay. Now after that, we can calculate the let's say mean squared error equal to the function we just imported, mean squared error. And then to calculate the mean squared error, you need two things, right? Y test, that's the observations in your test data set. Remember, when we do the train test split, Y test is the part of the target variable extracted as test data set for the target variable, right? So those are actual observations. And we just predicted based on Y pred. That's the output from the prediction method, right? And then that's giving you the MSE. Okay, we can also do the R squared, so we can do R2 equal to R2 score, and that's the method we had just imported, right? So again, we have to include Y test as well as Y pred. Okay, and run those, you will be able to get MSE and R2. Let's print them out. Okay. Print MSE and then followed by I2. And you can make it nicer by using F string and other things, but let's just look at the numbers. Okay. Well, the MSE is a very large number, which is not too surprising, right? Because it's a squared value. The R2 is 13.75%. Well, I will say that this is not a very satisfactory outcome, right? So usually, if you have something, the R squared value is a percentage. If you're close to 100%, then you are doing very well. If you are above 50%, maybe you're doing okay, right? But it's 13% is going to be a bit too low. Let me do one thing. When I import everything, let's also import math, the math package. Import math. Right? The reason is that other than MSE, let's also calculate something we call the root mean square error, right? Because MSE is basically a squared value, like the dimension, the measuring unit is dollar squared, right? If we do math dot square root MSE, we will get the dimension as dollar, right? That's more intuitive. So let's print our MSE, the root mean square value, which is the square of mean square value, to get some better idea, right? So, well, I mean, it's a $12,589, which is also a bit on the high end, right? So, I mean, it's very tricky to assess the model performance based on the absolute numbers you see, right? Because, yes, question.
For the very first one, for the Y prediction, should that be Y test or X test?
This, you mean the very first command?
Yeah.
It should be X test, right? Because you are predicting based on the features. You need to give the model your features, like age, BMI, and then it will generate the predictions on the bills for you, right? So you throw in X test, the feature variables, you get the target value as prediction. Okay? Yes, please.
So yeah, like in this case, based on the interpretation of your R square, right, which is only basically only 13% of the variance is explained by your predictor variables, right? I'm assuming one of the reasons could be because you only included 3-4 predictive variables as opposed to having your exhaustive list that you already had before, right? So like, if you were to sort of, you know, like looking at it from like a realistic perspective, would you stop right here and sort of go back and start adding more variables?
Exactly right. That's exactly the thing I'm going to do for the rest of today's class. So, I mean, whenever we see outcome like this, I mean, of course, we are not too satisfied based on the numbers, right? So, I mean, it's tricky in reality. You definitely need to try more, but if you can do better, that's not always guaranteed. Here, however, as a illustrative example, we probably know that we can do much better because among all those variables, there's something very important we missed, right? So, for example, there's something about smoker, non-smoker, which is going to be having a huge impact on health outcomes for individuals, right? So, of course, for other problems, it may be tricky. For some problems, it's inherently difficult, right? You may not be doing much better than a random guess. For example, if you're predicting if the stock price is going up or going down, that's very difficult. Otherwise, everyone's going to be rich, right? So, next thing is that we're going to look at the categorical variables. All right. So let's do the data frame again. Medcost.head to see what variables we omitted, right? So we removed all the categorical variables like gender, smoker, region, those 3 variables. Okay? The question is that let's actually focus on, let's say, Medcost region as an example, right, to explain how we can deal with categorical variables. So for regions, let's do the unique function. Okay? So we can see there are in total 4 regions: southwest, southeast, northwest, northeast, as the 4 possible values for that column, right? So we want to somehow encode the category variables as numerical variables. How do you think we can do that? I mean, those are string values or text values. How do we somehow translate them into numerical values?
If it's binary, you can assign it as 0 or 1.
Exactly, right? Binary variables are very helpful. For example, the region column basically asks you this question. What is the region in which the policyholder lives in, right? So that's a question you can answer to provide information for all the records. Equivalently, you can ask 4 separate questions. Combining them together will give you the full information provided by the region column, right? Because we have seen there are only 4 possible regions. Then we can use 4 different questions. First of all, we can ask, is the region of this policyholder southwest? Then is it southeast? Is it northwest? Is it northeast? Right? If you answer all those questions, it's equivalent to answer the original question of what is the region. And the benefit of break down the original question into 4 yes or no questions is that we can do binary encoding. Right? So then imagine we're dealing with the first 2 rows in the data set corresponding to 2 policyholders. For the first policyholder, I try to answer those 4 questions. And turns out the first client is in the southwest region. So I put 1 here and 0 for the remaining regions. That means the region of the first policyholder is southwest. Okay? And same thing for the second policy holder. For this customer, the customer actually lives in the southeast region. So then, is it the southwest region? No. Is it southeast? Yes. And for the remaining regions, 0 means no. Okay? So that's how we can encode the category variables by binary variables. Right? Binary variables, it's discrete value, but at least it's numerical value we can deal with. But there's still some redundancy. Actually, removing one of the column will not removing any information. Why is that? For example, if I remove the first column and keep the remaining columns, why do you think that does not remove any information? Yes, please.
Because whatever is left by default southwest.
Exactly, right? For example, if I remove the first column, there's no harm because I look at the first row without the first column. Right? It's not southeast, not southwest, not northeast. It has to be southwest. Right? So that's how it works. Because you have 4 possibilities. If you answer 3 questions, you can already find out the region in which the customer lives in. Right? So we can do the binary encoding. And furthermore, we can drop one of the columns. It doesn't matter which column you drop. So usually we will drop the first column because that's already implemented by some existing Python command. Okay. Now let's implement this idea. And this is, by the way, called one-hot encoding, right? Because you see, we are dividing or breaking down the original category variables into 4 columns. For every column, one of the values is 1, indicating the corresponding option is true for that record, right? So the remaining columns will have 0 values. Right? It means that one of the columns is hot, the remaining are cold. So it's called one-hot encoding. And to do one-hot encoding, we have a Python command comes with pandas. So that's get dummies, right? Those 0 variables we have seen those are somehow called by statisticians and the economists, they call them dummy variables, right? Because it's easier to answer the yes or no question than the what question, right? So it's easier for dummies to answer, I guess. Like that's why they call it dummy variables. Now let's do that, okay? So it turns out it's quite easy. And the way we're going to do that is that let's come up with a new data frame name. You can override the original, but sometimes I feel that I may need to go back to use the original data frame, right? So let's say metcast encoded. It's a new data frame after the one-hot encoding, and then I'm going to do pd.get dummies. Okay. And to get dummies, actually, I need to specify, which data frame to operate on. Okay. So it's actually the original metcast data frame that contains the category of variables, right? And then we will do drop first equal to true. That will drop the first, dummy variable for every category of variable, right? So just like we dropped the southwest column in the previous example. And let's try to see how it looks like. And there's one more thing actually we need to do after running this, but we can, to better visualize, we actually, let's use the head to display fewer rows, right? So the purpose is fulfilled, right? For example, for the gender column, for the sex column, now it's asking you if the gender is male, right? So we see true and false values, which is similar to what we have done before. But the difference is that we have true and false, those Boolean values instead of binary values, which is not good because we want to deal with numerical values, right? So we need to just add one more keyword argument, which is dtype equal to int. It means integer, right? So we don't want true, false, want integers. So we're converting true and false. Oh, yeah, sorry about that. Yeah, so now we have 0 and 1, right? I mean, it doesn't matter true, false, or 0, 1, but we need numerical values, so it's better to convert that into 0, 1, the integer values, right? False is 0, true is 1. All right, so that's that's how we can convert the data frame into a new data frame with the binary encoding for all those categorical variables. Now it's I mean, from the point of view of doing model training, we have all numerical values. That's a good thing, right? So it's about time to have the second break. So let's have a 10-minute break, coming back at 1:30, and then we'll quickly finish the training after encoding the categorical variables and see the difference. Okay?
What does it mean 0 for the sex and 1 for the sex? Could you know it's
Yeah.
for female or male?
Yeah, because if I don't include int, it's actually true and false, right?
Yeah.
That's very clear. But then if you convert the true and false to int, false is always 0, true is always 1.
False is always
0.
0
Yeah,
and true is always
yeah. So, I mean, I guess that's more like a convention, right? So it's
so like for here we imply that female is because female is the first value.
Yeah, yeah,
It's
it's-
so it can be 0.
Yeah,
And
yeah.
the male here is true.
Yeah,
and
so
will
it will be 1. Exactly.
So the first
Yeah.
value they come out,
Yeah,
they
yeah.
will be there.
I think for any automatic procedure in Python for converting those true false to 0, 1, it's always the case. Yeah. Okay, thank you. Okay, sure.
Will you be posting the rest
The
the Jupyter notebook?
Oh yeah, of course. I already posted it. So I posted a blank Jupyter notebook.
Yeah, I was following along with that.
Yeah. So you requested the recording in the first class, right? Is that you?
Yeah.
Yeah.
No,
Oh,
not
no,
recording.
yeah.
I emailed though.
Yeah. So, I mean, I did post a recording, like if you go to the course outline, but I think it's not very satisfactory because, it's a strange thing happening, not the whole screen not showing. I tried my best, but I
Yeah,
didn't.
it's easier to follow the-
Yeah. Bye. Have a good day.
So the newer languages are more integrated into
Yeah.
original languages.
because the applications are more complex and more varied. So you can cover a lot of bases. So Python's very good because it covers a lot of bases. But then C, you still have to see you have like regression of 4 ones who are very regression has translates the facts it does that for so that kind of thing doesn't happen. It's not good.
The layers that you
Low level, high level.
so high level is
The higher the level, the more inefficient it gets, like in performance, but easier to read and write. Microprocessor code. I studied it, I don't understand it. It's ridiculous. I'll show you. People used to. Yeah, they have.
So Python is considered one of the easier code to write with languages now, right?
Yeah.
I guess that people wait to be like just gonna talk about it. I don't believe it's a little bit.
Like it's being more. Yes. It's advantage. That's what we need. That's like this is what it looks like.
These are the statements that we get. MOV, something, 81.
They're
so
really
on.
very
This was the worst exam I've ever written in my life. I hated every moment of my life.
So the same thing that you presented in here, you can do in like other languages.
Just answer the question.
So C also does a kind of translation. C translates into
Yes.
C was created so
But
that
I do
it's
the other
easier.
way. I do the other way.
Yeah, like when it's like not or a line of code.
Yeah.
Then what makes sense you use
That's someone.
you need
No, that's basically.
okay, less text in C compared to this.
Yes.
Should make sense. It's like almost it's like $1,000.
You think that's right?
Is it a return or?
That'd be round trip. I think that's pretty normal. Actually, not that expensive. Browser boss environment.
Okay, let's proceeding to the last session of today's class. So before the break, we're talking about encoding this data frame to convert all the category variables to 0, 1 binary variables. Okay. And that is already done, and we have got a new data frame with all columns being numerical values. Let's try to repeat the procedure, but now this time for the encoded data frame instead of the original data frame with the categorical variables. Okay. So let's get the features and the target. It's easy to get a target, right? Y equal to med cost encoded, and then we're gonna do charges. Okay, and then for X, we can do med cost, again encoded, and this time we can just drop the target value, right? We're going to drop charges because that's the target, not part of the feature of predictors. We're dropping a column, so access equal to 1. And then the remaining things, this time let's try to keep everything. Okay? Of course, if you want, you can drop some parts of it. Okay, so that's to define X and Y. Let's try to run it first before proceeding further, so that making sure we're not encountering any errors. Yes, question? Oh yeah, so basically, if you do drop, it drops rows, right? So let's say drop 1, it means to drop the second row, because 0 is the first row, 1 second row. And then if you drop column, you provide the column name, but then you also need to tell Python interpreter that you want to drop along the second axis, right? Remember, along the row direction, if you're traveling along different rows, it's axis 0. Axis 1 is to, go from the first column toward the last column. Okay, thank you. Now we can do that train test split, right? So we're going to get X train, X test, Y train, Y test, and then we can do train test split. And this time we don't have to import those Python submodules. sklearn submodules again, because previously in the same notebook we have already imported them, right? So we're going to do X and Y. That's the two data frames. X is data frame, Y is just a data series, right? It's only one column. That's the stuff we want to split. And then test size equal to 0.2. Okay, so just reserving 20% as the test results. And random state is, again, you can use whatever you want, equal to 42. Right? But just to make sure that next time you run the same command, it will give you the same split. Now, let's again run it. No error, that's great. Now we can create and fit the model, right? So let's call it, maybe call it model underscore 1 to differentiate from the previous model, right? So linear regression, that's to create the model. Right? Very simple, even no data needed at this stage. But then model 1, we're going to predict on the fit, actually. We haven't fitted, right? So model 1.fit. And then we're going to fit on X train, Y train. And those are not the original X train, Y train. I have already overwritten the original X train, Y train by the second train test split, right? So that will do the split and model creation and fitting. We see that it gives me this two-row table, meaning that things are completed smoothly, right? So now we can do prediction. So Y pred equal to model 1.predict. And then we're going to predict on X test. All right. So again, this is the prediction part. For every row feature, every row in the test data set are focusing only on the features, we can get a prediction of the Y outcome, which is the medical charges, right? And run it again, no error, that's great. So then we can calculate MSE. This time actually let me directly calculate RMSE, right? So it's gonna be mean squared error. And we need to compare Y test with Y prediction. And then I can do mass dot square root to calculate the root's mean square error. And then we can also do R2 equal to R2 score. That's the method for calculating, the R squared score, right? So now we can run it. No error, that's great. But finally, we need to print them out, okay? RMSE and R2. At this time, it's actually pretty good, right? So because, if we look at the rooted mean square, remember it was like 12,000 or something. Now it's at 5,900. I mean, still a large number, but you can never expect predictions to be very accurate in reality, right? Because you never know what happens with each individual. There's so many things not captured by the feature predictors in the data set. But the R2 score is very, very good now. It's actually above 80%, so it's a big improvement. Yes, please.
So for example, if it's anything above 70%, so would it be okay to say, okay, this actually, the model is sort of adequate to predict, or to predict the variance? Or
yeah, so I think it's based on the type of cluster. Right? So I mean, this kind of prediction models can be applied to so many different contexts. So typically, I think 80%, 70% may be okay. There's some rule of thumb saying that this may be okay, but it depends on the results. For example, there's some prediction on the medical imaging, right? So because you show the picture of maybe the X-ray scan of the chest of a patient to see that person has any tumor or cancer, other conditions, right? And that's going to be an easy problem because, think about this. If I give this task to a specialist, he or she may do a very good job, right? And then machine learning is supposed to do a better job, right? So then the bar is higher, maybe 90%, 95% is a satisfactory. Now if you're predicting the stock price, and then if you ask the analyst to predict the stock price tomorrow, I mean, you can't expect that person to do a very good job, right? So that's a difficult question. If you cannot expect specialists to do a good job, I mean, machine learning probably will also encounter some challenges as well. So it all depends. Some problems are easy, some problems are difficult. I would say for this type of problem, it's actually quite good, right? Because for medical costs, I mean, it's not too difficult, not too easy either, right? But if you can explain 80% of the variance, why people have different medical costs, I would say it looks quite good, right? But of course, you need to consult. I mean, here our focus is more on the methodology. Is it satisfactory? I mean, we need to consult with, maybe your collaborator, maybe the insurance company to see if it's good or not. Right? Okay, thank you. So, any other questions on that? We can view the model coefficients. I think the most important thing is the coefficients, even more important than the intercept, right? Because they have a meaning, especially for linear regression. Because we have seen the equation, it directly tells you something about the feature importance, right? If you have a larger coefficient for a variable, let's say age, it means that feature is particularly very important for making predictions. If age increases, if the coefficient is large, it means that the medical costs are expected to go up very quickly. So let's focus on the coefficients this time. So let's do model 1, right, dot coef underscore. And that gives you a list, right? So I mean, it contains all the information, but sometimes we may want to have a better kind of visualization because it's not easy to remember which coefficient is for which variable, right? So let's do this. This time we're going to create a data frame based on this list of numbers, right? So we're going to do pd.data frame. But pay attention here. This is a one-dimensional array, right? A list. So basically, arrays can be multiple dimensions, but for data frames, it's typically two-dimensional. It's a table structure, right? So I want to convert this list of coefficients into a two-dimensional structure, right? Right now, we see one square bracket. It's one-dimensional. I'm going to add another pair of square brackets around this list, and that makes it two-dimensional. You can think of it as a list of lists, but there's only one element, right? It's a two-dimensional array, but there's only one row. So let's print it out. That's nicer, right? But I still don't know which, coefficient is which. And there's a simple way to resolve this. So what do you suggest to match all those numbers with the corresponding name of the features? How do we do that? We should provide column names, right? But how do we get the column names? So let's do this. It's going to be column equal to x dot columns. Remember, x is the data frame. Right? X is the, after we drop the target variable, we have the feature vectors as a data frame. It has heading, right? So x dot columns give you the column names. And then it should be the same, providing this variable names for all those coefficients, right? So let's try to see. Now things are pretty much very readable, right? So now for every variable, we can clearly see the coefficients. Now looking at those coefficients, what insights can we possibly get? Yes?
So on the prior stage, obviously has a positive correlation,
Mhm.
and multipliers to 48.
Mhm.
Whilst on the other hand, so if you look at northwest region, southwest region, so that tended to have a negative correlation, meaning people that might live in those areas there, they probably tend to be more on the healthier side.
Mhm.
So that's why they're doing less. So stuff like that.
Yeah, pretty much, right? Exactly. Thank you for providing the insights. Yeah, pretty much as you said. So if we look at those numbers, if the numbers are large, I mean that has a big impact, right? For example, smokers has a very large coefficient, right? More than 23,000, right? So I mean that it has a huge impact on the medical charges, which is kind of intuitive. So it's good to confirm the intuition. And then, for example, we can see that being older or maybe suffering from some overweight issues or having more children will increase your medical bill, right? That's also kind of intuitive. And being male actually reduces the medical cost. What do you think? What do you think might be a possible interpretation? Well, it depends. I mean, we don't know really what's happening, but I think generally you can guess that maybe female actually take their health a bit better than males, right? So that's one possible interpretation. So, females may take better of their health, so they actually better utilize the medical resources, so they pay a higher bill, right? Okay, question?
No.
Okay, thank you. And then for the regions, among those three regions, we can see that probably being in the southeast region reduces the medical bill because it's the largest negative number. I mean negative number with the largest magnitude, right? So maybe that's a more wealthier region, or maybe people there have this culture of better taking care of themselves, to have better health conditions. Or it's possible that it's a less wealthy region, so people actually have the habit of not using the medical resources. I mean, it depends on what really happens, right? So the data gives you some insights. We need to compare that with the reality, maybe some interview survey to find out what really happens. So we have the three regions here. How about the first region we dropped, Southwest? Do you think that's going to have a higher medical charges or lower medical charges? Yes, please. It can be higher, right? And so why it is higher?
One of them has to be positive outcome.
Exactly, right? So if all those three are 0, it means that we're in the Southwest. Right? And then it's more like disregarding the previous features, we have the benchmark value of 0. And then if you switch to, for example, Northwest, you have a negative value, which is below the benchmark of 0. So for each of those three columns, in terms of region, it's actually lower than the column we dropped, right? Okay, so that's pretty much the kind of the part of linear regression we want to deal with. But maybe I think something I didn't include, I think maybe that's also something interesting. So it's actually pretty simple. Probably you already know it from before. So things are not always linear, right? So let's say I want to, if I run the model, I find that the model results are not satisfactory enough. Right? So maybe I can think of one reason. Maybe it's actually because you're using linear regression, right? Because things are not always linear. There are many possible ways to build nonlinear models, but what do you think is maybe a very quick and easy way to directly build on the linear regression models? What do? We want to make it nonlinear, but we still want to use exactly the same functions, same methods from linear regression. What do? Well, look at the predictors, right? So it's actually, the predictors are something maybe we can call natural predictors, like age, like BMI. Those has a physical interpretation. But if you only do linear combinations, then you don't have a nonlinear model. One thing we can do, for example, let's say med cost. Look at, let's say, BMI, okay? So that's the column BMI, right? So if you just plug it into the linear regression model, well, you just multiply that by a coefficient. But we can do something like, for example, med cost. We can create a column, let's say, we can call it BMI squared, okay, squared, equal to, raise the BMI column to the power of 2, okay? Okay, so that's how we do it. And then, let me actually do it again. So basically, we can now visualize the data frame. So using the head function. Okay. Now we can see that in addition to those natural predictors, we have an artificial column, BMI squared, right? So now if you plug the model into the linear regression model, you will have a coefficient for BMI squared. It's like we have A1, A2, A3. Right? Now we have A4 times BMI squared. And this term is the variable BMI being squared, so that's a nonlinear term, right? That's actually a quadratic term. You can do, cubic function. You can do, higher order of powers, right? So, or you can even do something like interaction, which is also fairly common, right? So let's say interaction of BMI and let's say children, okay? And that what we can do is take the BMI and another column, which is children. We can multiply them, okay? So then we have another column. Right? So we can introduce those terms. Then it will make it possible to include the linear regression equation some nonlinear terms. Right? So I think general, you don't want to use too many additional columns, right? If you probably, most cases, I think it's more than sufficient to consider the quadratic terms, right? Including the possible interactions and including raising a certain variable to the power of 2, right? So then you can try to do those kind of experiments and then try to figure out if you can improve the performance. Not always, right? If you actually make the model more complicated, it could be a bad thing, right? Because it leads to overfitting, right? Let's say you only have a few rows of data points, then you make the model very complicated. It will cause overfitting, right? Because it focuses too much on perfectly fit the training data. It may perform poorly on the test data. Question?
Yeah, like, so in this case, you kind of like amplified the impact of BMI by increasing its magnitude by 2, right?
Mm-hmm.
I'm just trying to understand the practicality of it. Why would anyone want to take that approach?
Oh, well, first of all, this is just one thing to experiment on, right? So it doesn't hurt to try it out. Here, just an illustrative example may not be the case. But you're right in the sense that normally you want to build some intuition. So for example, I think it's more common to assume that maybe h squared, right? So maybe because, as you age, if you are, let's say you're 30 years old, after 10 years you're 40 years old, well, health in general will deteriorate, but maybe not too much, right? Because you're still a healthy adult in general. But then if you're turning into 90 from 80, it's a big difference, right? So the intuition is that it's not supposed to be linear, right? So the medical costs should go up very quickly, intuitively, if you actually age, right? So especially when you are old enough, then you further age, the health condition may deteriorate much faster than when you were younger, right? So then maybe a good idea actually to square the age. BMI, well, because it's more like a small range, right? Because it ranges from maybe typically 18 to 30 or something. I think it may not be making too much sense to square BMI, although here I just use the illustration idea, right? And then maybe due to some reasons, let's say being a smoker as a young person, being a smoker as an older person, right? So that maybe have different implications for your health condition. Right? So basically, it may be potentially interesting to see, should I do the interaction between age and smoker, right? Or gender and smoker, right? Because smoking may affect male and female differently, right? Because I don't know, maybe because of medical research results or something like that. So it's never an easy question. So I would say that linear regression is always one of the easiest tools to use. So always try it out and see how it performs, right? And then if you want to make it slightly, improved, right? So if linear regression performs reasonably well, but you want to see if you can do a little bit better, maybe try the quadratic regression by introducing the quadratic terms, right? And then if you want to do even further, well, you can do the cubic terms and so on and so forth. But in general, I would say use like decision trees, random forests, and neural networks, those more advanced models.
So yeah, I guess like in this case, obviously like when people age, right? So based their probability of getting the diseases and stuff obviously increases as well. So this is sort of like a combination of math and intuition, right? So and I guess like the overall intent would be to, for example, we were at like 80% R squared value, right? So by adding these factors, so you can probably get to like, I don't know, 90%, 95%. This is kind of why they would want to do that?
Yes, possibly, right? So it's always useful to experiment. So basically, those are the basic but important methods like linear regression, right? So many methods build on top of that idea, like generalized linear model, and make it, including polynomial regression, make it slightly better. And people are always interested to see if I can do a bit better. Other questions? Yes, please.
How would you know if your data is like too well modeled to the training data? Then it's just the level of variance that you drew up. Like.
Oh, sorry. What's the question?
So how would you know if your data is too well modeled to your training set, so that it's going to perform poorly on your test set? You said there's a certain level. Like I just want to know how you.
Oh yeah. How do you know that it will perform well in the training set?
Yeah.
Well, Well, not necessarily. We can perform poorly in the training data set as well. Because, it depends on the structure of the data, right? So if the data is not going to be captured by the linear models, and then even for the training model, the training error is going to be large, right? But the idea is that if you use very, very complicated models, let's say you have very complicated polynomial functions to model the relationship, you can do very well for the training data set. Because you make the function so complicated. Right? So there's a mathematical theorems and observations that polynomial functions alone can already approximate any complicated functions, as long as you have adequate terms in the polynomial function. So if you make the model complicated enough, we can do very well in training error, but still perform poorly in testing error. So not necessarily you can do well, but in general, you will do better in training than in testing, right? Because training error is something the model wanted to minimize. It spent effort minimizing the training error, right? So that's something done by the model. So it's going to be at least somehow better than the testing error. Testing is completely unseen by the model. Right? It's something similar to the future, to the model. So it's generally going to be worse in terms of testing error. Yes.
So in a specific case, like, for example, if we were to turn this into a polynomial model, right?
Yeah.
So let's say like sex and then children and smokers. So we can kind of combine those three factors as well, and then to improve, the predictability factor.
Yes. Yeah, exactly. Intuition is helpful, so you can decide which interactions you want to pick, right? But I believe there's also automatic procedures for you to, create all the interactions and all the square terms. Right? So I don't remember that particular command, but later on I can provide some information on that as well. Yes, please.
So after training your model, if you use two different data sets to test it, the accuracy will be different for the two separate instances, right?
Exactly.
So so in practice, do you test it multiple times to make sure that it's not like a fluke? How would you know?
That's an excellent question. Right? So there's a method called cross-validation. So I guess you can apply it to regression, but later I will spend effort and time on classification problems, because most of the projects are about classification problems. So if you train once and test once, in general, it's not that reliable, right? Because how do you guarantee that it's also going to be performing well on other test data, right?
Yeah.
So the idea is that, for example, you can have a 5-fold cross-validation. You have a data set, and then I cut it into 5 equal portions, right? So then you reserve 1 out of the 5 portions as testing data. So the remaining 4 as training data. So that's called, so that's something like 80%, 20% split, right? But you can do something similar, but using different portions of the data set, right? So I use segment 1, 2, 3, 4 as training, and segment 5 as testing. Right? And next time I can do segment 1, 2, 3, 5 as training, segment 4 as testing. You can repeat the whole procedure once again, right?
Based on the same overall data set, but like.
Yes, because you have. If you have more data, you can do things differently. But typically, you only have a single data set, and then you want to make the best use of the data set. Right? It's also equivalent. If you have several data sets, combine them together to form a big data set, and you can do the cross-validation. Right? And then you can do different assignments. So you can do segment 2, 3, 4, 5 as training, segment 1 as testing. Right? So every time you will get a different testing error. But then you do it multiple times, you will have a list of test errors forming a sample, right? You have a sample of testing errors. That's something telling you the distribution of testing errors, not only the single testing error value. Right? So later on, we're going to come to that. Okay. All right. So we still have a little bit of time, so we can proceed just a little bit into the next part, which is classification. Okay. So let's maybe do like 10 minutes or so to go over some of the concept and theory parts of classification. so that next time we after midterm we can directly jump into the coding. Okay. So we have regression and classification. The difference is pretty clear, right? So if we're predicting continuous value like costs, price, that's regression. If we are doing classification, it means that we're trying to predict which group or which category or class a certain data record belong to. Okay? One example. So let's say, we all need to choose our internet plan, but usually the service provider offers a list of options, right? And then from the point of view of the service provider, I want to predict if a customer would switch to a basic plan or a plan with unlimited data or another possible option of the plan, right? It's going to be several categories, and then I want to predict a potential customer with a certain characteristics, which plan would she or he choose, right? So that's a classification, because there are several possible outcomes for me to choose from. Later on, we're going to work on this data set, predicting patient show or no show. Right? A patient goes, makes an appointment to go to see his or her doctor. At the appointment date, it's possible that some patient will not show up. Right? Just like a class, some of you show up, some of you do not show up in the class. It will be interesting for the stakeholders to predict the probability of a person being a no-show or being present. Right? So again, show or no-show, 0 or 1, that's a classification problem. And a lot of those things going on. If you give the computer a picture of an animal, is a cat or a dog, you choose from certain categories. Right? So let's say Tesla's self-driving, you're on the street and the camera detects an object. Is it a pedestrian, or is it animal, or is it just a trash can, something like that? Right? Like email being a spam or a normal email is a fraud. And so there's possible labels we already know as the possible outcomes, and want to predict one of all those possible labels. Right? So that's classification. And the format of the data is typically that in each row we have, again, features and the target variable. Right? But the only difference is that the target variable is discrete. It's indicating one of the possible classes. Okay? We want to, typically do prediction. It means that we want to predict the outcome, right? If a picture is a cat or dog, I'll just give you a prediction. Like, is this patient going to show up for his or her appointment at 0 or 1, right? But it's not always realistic. Right? Typically, it's not realistic. Right? I don't know beforehand a person will be showing up or not showing up. Right? For those kind of problems, sometimes it's better to predict the probability. Right? So let's say, I know this patient made an appointment like 2 weeks ago, and he's suffering some conditions regarding diabetes, and along with some other additional information. And given those information, I want to say, what is the probability of this person showing up on the appointment day? Right? Because that's going to be providing more realistic and more useful information. This is an example, let's say, in the context of applying for a loan, like say a mortgage or other kind of loans, right? So the features, of course, will have multiple dimensions, but let's say we only focus on 2 dimensions. The debt, monthly debt of the person, and the monthly income of the person, right? So if we want, we can produce a scatter plot, okay? And then the coordinate of each point in the scatter plot will be the debt and income monthly. Okay? But in the data set, we'll be provided the labels of the outcome, right? So maybe for some people the loan is approved, for some other people the loan is rejected. We can use different color, different shapes as what we have seen in our assignment and also other examples for scatter plot, right? So given these labels, I want to figure out a way to divide those points and other possible points into 2 groups. Right? A simple way not necessarily the way we are going to use, but the simple way is that maybe I'm going to divide the whole space into 2 segments, right? So then, even for those points not in the data set, let's say the data point here, a person with a monthly debt of 25,000, a monthly income of, let's say, 10,000, right? So then we can classify that it's in the region of squares, or in the region of most squares, and the loan will be approved, right? So classification is basically, divide all the possibilities into several groups or several regions. Right? And speaking of, let's say we are given characteristics and the class labels from the data set. Let's say we have 100 data points in this data set. Then for every point, we have the information of the loan being approved or not approved. Right? Now, for what we want to do is to predict based on new data points. Let's say we have another data point. Let's say application or applicant 101, not in the data set you have. That's a new client, right? So what we want to predict essentially would be what is the probability of this person's loan application being approved, like, or being 1, right? Typically 1 is positive, and 0 is negative, being declined. Okay, so what is the probability of approval and rejection? And those 2 probabilities will sum up to 100%, right? Because there's only 2 possibilities. Same thing, I want to predict the possibility of other applicants, right? If you have more new applicants arriving, then for every applicant, I want to predict the probability of that application being approved or declined. Okay? So another question is that if I can accomplish this, if I can predict the probabilities of any new data points, right, then how do we label those applications? I mean, we know the probabilities, right? But if the manager says that you have to give me a binary prediction, 0 or 1, and then how would you predict? For example, let's say this applicant number 160, right? The probability of rejected is 40%. The probability of approval is 60%. And then how do you predict?
So, in binary terms, you could say that like the prediction would be that it gets approved, or you can say it in terms of probability that there's a 60% chance of it.
Exactly, right? But if I have to do a prediction, right? Because
if it's more than 50% likely, then
yeah,
you say that it will.
Exactly, right? So naturally, if it's more than 50%, then I can predict approval. Right? Of course, it depends on your risk attitude. Maybe I want to be more, I want to tell the applicant that your application is likely to be approved. But maybe I'm conservative. I'm saying that I'll tell you that only when the chance is higher than 80%, right? So you can choose your threshold. So the main idea is that first we do the probabilistic modeling and prediction. Once we get the probabilities, we can choose a confidence threshold. And typically, or most commonly 50%, but you can use different thresholds. The prediction outcome will be changing, right? Depends on your need. You can use different thresholds. Okay. Later we'll see that if you use different thresholds, the outcomes will be different. And the performance outcomes will also be different, right? Maybe the performance of correct predictions will be increasing from, let's say, 60% to 70%, right? Maybe it's going to be reducing, right? So that will have some possible implications, and we'll actually spend a bit of time on those kind of things. Okay? Now, when it comes to classification models, there are many possible methods. Right? I listed some of them. We're going to start with, I think for those three methods listed here, we're going to cover all of them. Right? So logistic regression, k-nearest neighbors classification tree. If we have some time, we'll look at other possible methods as well. Right? So one thing to think about is that, not think about it, but to notice that typically, let's say if we're doing logistic regression, it's typically for binary classification, right? So either 0 or 1, approval or rejection, show or no show. And with the threshold combined with the probability values to make a prediction. Okay. The question is that we introduce linear regression, and logistic regression is going to be another method that's built on the idea of linear regression, as we will see when we dive into more details. So a simple question for us to think about is that why do we not actually directly use linear regression? Why not linear regression for classification? I mean, we're predicting, let's say, binary classification, 0 or 1, right? Yes or no, show or no show. So why can't we directly use linear regression? Yes, please.
I'm just gonna say because it doesn't give you a binary output.
Yes, that's the main idea. So because linear regression gives you continuous quantity, that's why it's not for classification. But why do we not use? I think there's some issue with my charger. Why do we not use linear regression to predict the probability value, right? Probability of the loan being rejected. But that's a continuous value, right? So why not? So, well, probability is between 0 and 1. But linear regression models use a linear function. Linear functions are typically not confined between the range of 0 and 1. Right? So if you have a linear regression, let's say in a one-dimensional case you have only one feature, it's going to be a line. And if the line is trending upwards, then you proceed farther enough along the feature space, feature dimension, you will eventually exceed 1. If you're traveling to the left, it possibly you will drop below 0, which is not good for probability values, right? So we need to. The idea of logistic regression is that we're going to transform the linear function into a nonlinear function, and more importantly, the nonlinear function we want to use is always going to be taking values from 0 and 1, right? So there are several steps. First of all, we just use linear regression based on the features, x's are the features, right, to predict a quantity. And that quantity can be anything because it's a linear function. Then we're going to apply the value of fx, the intermediate quantity, to a function we call the sigmoid function. Right? Once you get the value of f, I will do e to the power f divided by e to the power f plus 1. E is a constant number, approximately 2.73, right? Based on the natural logarithm, some math that is not too important. And then this value is always going to be between 0 and 1, so it's suitable for predicting probability. Interestingly, that's actually the most simple kind of neural networks we can have. Right? So sometimes people call this form of functions with the perceptron. Right? And then build on those kind of functions, we can get linear, even neural networks. So to visualize, this function will have this nonlinear form, but nicely confined between 0 and 1, making it suitable for modeling probabilities. Right? And an equivalent form of this sigmoid function is listed here. Right? On the right-hand side, we have a linear function. On the left-hand side, we have a logarithm term with the argument of probability over 1 minus probability. That looks, maybe to some of you may look familiar, right? Sometimes we call this the odds. The odds of winning, losing, odds of being 1 or 0, very common term in terms of election and gambling. So it means that even though we're not modeling the probability directly as a linear function of the characteristics, features, but what we're doing is to model the log odds as a function, as a linear function. So it's essentially still a linear regression, right? So we are going to model the log odds as a linear regression model. So that's the main idea of logistic regression. And logistic regression is typically used for binary classification. But it can also be generalized to do classifications with multiple classes as well. And we're going to lightly touch on that.